Hey, good afternoon. Thanks for coming. This talk will be about full disk encryption and the realities of secure storage on mobile devices. I'm Daniel. I'm a principal consultant with the NCC group. So basically I do all kind of pen testing and software security assessments, but I have a focus on the iOS side, and I've written a tool called IDB, which some of you may be familiar with for doing iOS pen testing. And I give the talk together with Drew over here.
Thanks. Yeah, my name is Drew. I'm a senior security consultant and research director with the NCC group. I also have extensive background with the CyanogenMod project on the open source side, bringing up new devices and unloved devices, as well as building out the wiki and exploit database for getting Android onto your phone.
And in case you're not familiar, NCC Group is a UK-based company, but both of us are out of Chicago, and we have a number of offices in the US. Both of us are in the pen testing practice, but we also do software escrow and domain services, and a number of different other areas where we're working in. So, quick overview, giving you a brief introduction into the topic and why it's important. Then I will be talking about secure storage on iOS and tell you what functions are there, how it works, and what the different features are. And then Drew will take over and talk for the bigger part of the talk over secure storage on Android and how it compares to Android. We'll also show you an exploit, how full disk encryption on Android may not always be as secure as you think it is, and then give you some outlook on what we think, where we can go from here as an industry. So why do we talk about secure storage? You probably recently have seen the FBI San Bernardino case against Apple, and that's just like one example on why people are interested in securing data on a mobile device. And traditionally, we have data stored on a server where we have tight controls, where we can have it in our data center, and we know exactly where the data is and how to get to it. But on a mobile device, the data is on the device, and it's being carried around, and it's mobile. So it's much harder to actually enforce controls on where your data is and who has access to it. And if you look at how people use mobile devices, we see that they're mostly using applications. So if you have some graphs, you see that 90% basically of people are using mostly apps on their device and not using the mobile web. So they actually have apps which are able to store data on the device, which may store data there. And then, so the problem is, we need this mobility, right? That's the purpose of these devices. So the data which we have is being carried around constantly, and that exposes them much more than previously. For example, here's some statistics from 2013 in the US. There were 1.4 million phones which have been lost, and 3.1 million phones which have been stolen. And while those probably were not targeted stolen phones, you could imagine somebody targeting you to get your data and stealing the phone. So this is something we need to consider as an attack vector. And what makes this all pretty challenging is that while we need to secure the data, we also need to make it accessible. Accessible meaning the data has to be there if the user wants it. So if we're caching data on the device, so that if you're on your airplane, you can read your emails, or you can read a PDF, read documents. If you want to log in into your apps, you don't want to type usernames and password every time, so we need to store access tokens or credentials in some way or form on the device. And we have to do this in a way so that we actually make it usable for the user. So we don't want to have security controls which are so burdenful to the users that they either disable them or get around them. So we need to find a trade-off between all these different things so that we don't end up coming up with an absurd procedure like in this comic.
Thanks, Daniel. So everyone's heard the phrase, there's no such thing as absolute security. But let's take a deeper look at who you're actually worried about looking at the data on your device. So we'll go through a couple categories here. So the remote attacker, this is someone who wants to connect to your device remotely over the internet. We have the coffee shop attacker, which is something like you're in a Starbucks and on an insecure Wi-Fi, and somebody might be intercepting or modifying the traffic you're sending. Then the casual thief, someone who really probably doesn't care at all about the data on your phone, but they want the hardware to flip and make a quick buck on that way. And then targeted attacks, someone who's specifically coming for you, specifically, and the data on your phone. And then finally, nation states, which have a much higher budget and time to make targeted attacks against you. So if we kind of put these on a graph of sophistication and effort, we can kind of see, obviously the casual thief is very unsophisticated and requires very little effort to snatch something from you. And all the way up to nation states, the sophistication is much higher and much more effort involved to do something like this. And so the defense against these sort of scales along with this graph here. And it's important to kind of know who you're actually worried about looking at your data. So we'll talk now about mobile data security. A quick intro to full disk encryption. Files are transparently decrypted when they're read and transparently encrypted when written to application sandboxes, for example. And the protection really only exists when the device is off, in combination with a strong passcode, of course. But we need something more fine-grained and more control here. This is very binary, on or off. So with that, we'll look at how that works on iOS, and Daniel will tell you about that.
Thanks. So in iOS, really the whole process starts at boot time, and we will talk about the Android side about that and how things are different there. So in iOS, Apple has the big advantage that they produce the hardware and they produce the software. So they can build hardware support for certain software features. They can build software support for the latest hardware. So they can, for them, it's much easier to build these systems from the ground up and make them secure all the way through. So they verify the entire boot chain. There is a hardware root of trust, which is a public key, which can be verified, which is baked into the hardware, and then the entire boot chain from the bootloader over even the baseband and kernel and everything like this will be verified when the system boots up, so we know that we have a trusted system running. And then when you install updates, that's the same thing. All the updates have to be signed by Apple. If you've ever tried to install an iOS 8 currently on an iOS 9 device, you will notice that you cannot do that anymore, because every time you install it, there's like a challenge response kind of protocol where your phone actually phones out to Apple, and they need to sign it specifically for your phone in order to install it. So you're not able to downgrade, and so you're only able to install the latest version which Apple deems current or secure for you to be used. And then now that we have a running operating system, all the apps on top of that are also signed. So through the App Store process, all apps are also signed by Apple. And so we kind of know where all software which is running on that device is coming from, since everything has been signed and there is no way to bypass those checks in the ideal case. Now that we have this, let's talk about how we get secure storage and encryption on there. There's a few key components which we need to actually make that happen on a mobile device. The first thing is we need to have a device passcode. We need something which is not stored on the device, because if it's on the device and you steal it from someone, then you have the encryption key and you have the data, and you haven't made any progress there. So the device passcode is used to derive an encryption key whenever you type it in, and then that key is used to encrypt data which is on the device. And then when you lock your phone, that key can be wiped from memory, and it will not be on there until you unlock it the next time. So you have protection from the time the user unlocks the device till it's being locked. So that's like one step further than what we had from full disk encryption. The problem is that users choose really weak passcodes, 1, 2, 3, 4, or like some sort of patterns on their keypads. So these are prone to offline brute force attacks. If you just copy the data offline, and then you can brute force the passcodes. So in order to prevent that, we need to rely on some hardware. The way this usually works is that there's some sort of hardware root of trust in the device. On Apple's side, there is a unique encryption key which is baked into hardware at manufacturing time, and that key is not readable from software. So you can't read it out and copy it off. Any operation involving this key will have to be performed on the device. And so that kind of ties you to the device for brute force attacks. And since you need to use this hardware component, you can actually have brute force control. So you can say, oh, after a certain amount of times, we delay you by hardware, and there's no way to really bypass that. Similarly, you can enforce device wipes, because you can in hardware count how often you try to unlock a device. And if you hit a certain threshold, you could just delete all the encryption keys and prevent access to the data forever, basically. So now that we know these two concepts, let's see how this all fits together in the iOS encryption scheme. This is for the file encryption. I will talk about the keychain right after this, because they're kind of related. So down here in the corner, we have a file. And every file on iOS has a separate file key under which it is encrypted. And that file key is just stored with the file metadata. So it's just on the file system. So it doesn't really help you all that much if you would store it just that way. So what happens is that we have a file system key, which is unique for every installation of iOS on your device. And that key is used to encrypt that file key. So that file key is protected under the file system key, and then that file system key is protected under this hardware key I've been talking about. So we basically tie this file key via the file system key to the hardware. So you can't decrypt it off the device. You can only decrypt it on the device when you have that hardware key available. That doesn't really help you much if you steal the phone, because then you have the hardware and the key in the file, and you can still decrypt everything. So that's where we need to have the passcode. And the passcode is used using pbkdf2, which is a key derivation function, to derive a passcode key. And then that key, together with the hardware key, is used to have like another bunch of keys, which we'll talk about in a second. And those are then used to encrypt the file key. So you have something which goes into the file key encryption, which comes from the hardware, and you have something which comes from the passcode. So you tie it to hardware and to something the user knows at this point. So let's look a little bit more at why we need this file system key in the first place, because you could just use the hardware key. The main reason is that if you want to delete your iPhone or iPad remotely, for example, or after some encryption attempts, you can just delete that key, and all your data on the file system will be inaccessible. You couldn't delete the hardware key because that's baked into hardware, so you need to have some intermediary key there. So this here, it looks a bit complicated, so let's look at this into a bit more detail to see what's going on here. So there's basically 3 different class keys, and they're called NS file protection none, NS file protection complete until first user authentication, and NS file protection complete. And they kind of do what you think they would do. I don't know if it's intuitive for you. For me, I had a hard time figuring that out the first time. But the idea is that the first one here, the NS file protection none, is only tied into the hardware key, and it's not tied into anything else. And the other 2 are actually also using the passcode, but in 2 different ways. The first one will keep data encrypted until you unlock your phone the very first time when you boot it up. So if your phone is off, you turn it on, and then its data is still encrypted until you type in the passcode, and then that key is being generated and kept in memory until you turn your phone off, basically. So that's kind of similar to what full disk encryption traditionally does. And then the second one, they are complete, is the one which is being wiped from memory every time you lock your phone. So that's a much stronger protection, because if your phone is locked and somebody gets it, that key is not available to them, and they will not get to data which is encrypted under this. So these are the 3 main categories which iOS has and that you can choose from as a developer when you implement things. And then talking about the keychain, which is just a way of storing smaller amounts of structured data on the device if you don't need files. That one actually functions quite similarly. And internally, it's just a SQLite database, which is on the file system, and every piece of information you want to store on there is just an entry in that SQLite database. But every entry is encrypted individually depending on when you have access to it. So it uses similar things. I have a table in a second. The main problem with it is, though, that if you uninstall an application, it does not delete the keychain entry. So you may have an app on there which you tried a year ago, and that keychain entry is still on there. So if it's a later point in time, if you sell your device and you don't wipe it, or if somebody gets your device or borrows it, they may get access to whatever you had in the keychain at that point in time. Internally, it looks very similar to what we just talked about for file encryption. On the left side here, you have the list of the 3 categories for file encryption, and the middle column is the equivalent keychain class. They also have nice long names: case header accessible always, after first unlock, or when unlocked. And I think they're a little bit more intuitive, but they're exactly what you expect what the correlation for the file system one was. There's an additional category called when passcode set. And the reason for that is if people realize if you're an app developer and you want to store data on the device, and we now learned that you need to have a passcode for actually having security on there, you don't know if you cannot enforce that your users have passcodes on their devices. So what do you do in that case? Do you still store the data? Do you want to warn the user? Or do you just want to just ignore it, basically, and not store and have like a usability problem? So with this function, you at least can check what's going on, and you can only store data if the user has a passcode. And that's available since iOS 8. So you may wonder, why do we need all of these different categories in the first place? Why don't we just have the most secure one for all data which we store on the device? The problem is that we need different data available at different points in time. If you turn on your phone, you kind of expect that you can receive phone calls at this time, or text messages, or that you can use Find My iPhone to locate your device. So certain functionality just needs to be available always when you turn your device on. So that data cannot really be encrypted at that point in time. Then similarly, There's others which you can protect a bit more. If you don't necessarily need to have your contact or Wi-Fi credentials available right away. It's okay to unlock your device once first, and only then you have those available. So Apple chooses to encrypt certain things by default, and in this category after first unlock. And then again, even others such as Safari passwords. You don't need to have your Safari passwords available when your phone is locked because you don't use Safari at that point in time. So those are even stricter protected. And these are just examples from the stock applications on how they're being used for these categories. But if you're an application developer, you can choose to do similar things. If you need data for push notifications, you may need to have it accessible at certain times, or background jobs. Other data you may restrict to only have it available when the user unlocks the phone. And that kind of gets us to usability, because there's kind of always a trade-off between when are things available and when they are not. So if you want to make it easy for your cat to get to your phone, like on this video, you probably use Touch ID. So Touch ID was kind of misunderstood in the beginning because everybody thought, oh, I can just lift somebody's fingerprints and I can get into the phone. But actually, it's meant as a usability feature, and it actually coerces users to like, oh, maybe I should put a passcode because Touch ID is awesome and I want to use Touch ID. And when you want to use Touch ID for payments and things like that, you have to have a passcode on the phone. And here on the bottom are two slides which are probably hard to read. They're from Apple's latest keynote from WWDC this year. And they showed that before they had Touch ID, only about 50% of users had a passcode on their phone. And since they rolled out Touch ID, it's up to 90% of people. So 90% of iPhone and iPad users now have a passcode on their device. And it's mostly because Touch ID makes it easy that you don't need to type it in every single time. And so Touch ID, you know it to unlock your phone, or you know it maybe for Apple Pay if you're using an iPhone. But you can also use it as an app developer to have another level of control over your data. You can tag a keychain item using access controls and can say, whenever I read or write that keychain item, I want the user to re-authenticate. And that can be either by swiping the finger, or it can be by typing in their passcode at that time again. So you can have data explicitly authorized by the user, even if the phone is unlocked already. And similarly, there is a local authentication API, which is an OS level thing, which is not tied into the encryption directly. But what it does is basically asks the operating system, hey, can you ask the user to swipe their finger? And then it comes back with yes or no. The problem with this is that if you have a jailbroken device and you can hook those operating system functions, you can pretend that somebody swiped the finger successfully and the app will believe it. Well, for the keychain one, it's actually tied into the encryption and it's all done in hardware, so you can't really hook those functions and bypass it. So the user presence for the keychain is a stronger mechanism than only using the local authentication one. So where does this leave us with the threats you can still have after you do all these things? Jailbreaks are probably the first thing which come to mind when you think about things that can go wrong with iPhones. So jailbreaks let you do arbitrary execution of unsigned code on the device. Before we talked about everything has to be signed. If you jailbreak the device, those things are being patched and disabled, so you can run arbitrary code. It does disable some OS level protections in order to get the code running, which you need to have to disable those things. But they don't necessarily disable sandboxing of apps. So if you have two apps, they're still sandboxed. You could disable the sandboxing, but the jailbreak does not necessarily mean that the sandboxing is disabled. So you still have isolation between applications potentially. And regarding secure storage, well, so first of all, if you have a passcode on the device and you ever try to jailbreak your phone, you may not be able to do that with a public exploit because that requires you to reboot your phone like 3-5 times, and then you need to type in the passcode every single time. So you may not be able to use a public jailbreak, but there may be people which have jailbreaks which don't require that. And in that case, data which is protected under the passcode or fingerprint are still secure because you can't get to it without knowing those keys. But what's still possible, though, even on a non-jailbroken device, is that you could have a malicious application who can access personal data. They can just be privacy infringing and just asking for too many permissions. Or you can have apps attacking other apps via inter-process communication, calling URL handlers and getting data from other apps, which are more like app-level flaws, more or less. It's not really like an iOS issue. And then a topic which we will talk about in the Android side a bit more. You could jailbreak a device and you could backdoor it. So you could install something in the kernel or in an app which monitors the user's behavior and steal some data. And we will demonstrate it in a bit. And with that, I'm going to give it to Drew for talking a bit more about Android.
Thanks, Daniel. So let's look at how Android handles the similar things that Daniel just talked about for iOS. Here's a table of the evolution of Android security that we put together. And in particular interest to this talk are the items in blue, which pertain to secure data storage. But as you can see, a lot of security features have come with each revision of Android. You get a little bit stronger, a little bit better. There's two on there that are probably hard to read, but the key store hidden keys and force encrypt have asterisks next to them because Google tried to roll this out with Lollipop and realized their OEM partners weren't quite ready for that, so they rescinded the force encryption that Lollipop was supposed to come with. That is now mandatory in Marshmallow and beyond, but one thing that's interesting to point out there. And then the newer things for 6.0, the fingerprint API and verified boot, which we'll talk a little bit more about coming up. So if we look at the adoption of Android as a platform, there's kind of an issue with the fact that most people are still on an unsupported and insecure version, which is KitKat there, and you kind of combine all the different versions there. That's an issue. This graph actually looks much better now than it did a year ago because there are a significant amount of people on the latest version, which is good, and this progress is happening here with Android fragmentation. But if we kind of snap back to iOS a little bit, it's very clear that majority of iOS users are on the latest and thus most secure version of the platform. So how does this have an impact on application developers? Because there's so many different versions of Android with so many different security features coming at different times of the platform, there tends to be a lot of code complexity needed to develop Android applications because you can't necessarily rely on your app running the same on two different versions of Android because they may have better protections available in a newer version that you can't leverage in an older one. So this kind of leads to a lot of like if-defs and code complexity and inconsistent behavior as a result of this because if you don't trust the platform at a certain version, you're going to have to like hack around that essentially as a developer. And access to more secure functionality is not necessarily available for all users. So things like hardware-backed crypto storage may not exist on your more budget version of an Android device as opposed to like a flagship model which would have that. So developers need to sort of like query via API to see if that's available and then do it in a more secure way. And if it's not, then you get what you get kind of thing. And security improvements are available only in the latest versions that come out. So Android has a long history of complicated OTA problems. Devices that come out and just never get an update and never get supported, or ones that get maybe one or two updates but are left behind. And these devices live for quite a while. I mean, most people probably have devices longer than a year unless you're really into phones. So these kind of problems live for quite a while out there in the wild. So let's look at how Android encryption works, similar to how Daniel showed it on iOS. So when you enable encryption or when you boot a newer phone for the first time, the DEC or device encryption key is set and encrypts all the disk sectors on the volume for user data. And that uses AES CBC 128. But we have an issue with, what if I want to change my password? So we have the concept of a key encryption key, or KEK, and an initialization vector together form what's called the encrypted DEC, which is then stored in a crypto footer, and I'll talk more about that later. But the reason this is relevant is because if you have a passcode and you want to change it, you don't want to have to re-encrypt all the data on your volume again. So essentially, the key encryption key can change, and that's fluid, but the device encryption key is set once the encryption is enabled for the first time, and that stays persistent. So similar to how iOS, we take user input, and depending on the version of Android you're running, it's PBKDF2 derivation function, or more modern versions use scrypt for better security. But this can be a PIN pattern or passcode. This is sort of run through the derivation function, and then you get your key encryption key. Something that Google added in 5.0, Lollipop, was the ability to have this hardware bound. Thus, there's a unique ID for every device, and the key encryption key can be wrapped and signed by this built-in function in the stock. Unfortunately, I don't know if you guys saw maybe a week or two ago, A researcher discovered that this is actually not hardware bound, and this key is accessible via software. And so by exploiting trust zone, you were able to recover this key and thus sort of render this not as effective anymore. And the blog is down there. It's a very complicated post, but it's very interesting to read, so I encourage you to check that out. So back to the crypto footer. The encrypted deck is stored, and it's usually carved out of the end of the user data partition. Some devices have a dedicated crypto partition for this metadata. But Android's encryption only protects one partition on your entire device, and that's the user data partition where all of your settings and user downloaded apps and everything go. But that leaves the boot and system unencrypted, and we'll see why that matters in a little while. But if you're familiar with Lux, it's Lux-ish, but it only has one key slot, so you're essentially bound to have a single password for your lock screen and for boot. There are a lot of custom modifications that people put into things like CyanogenMod or other custom ROMs that let you have more key slots, and thus you can have a much more complicated boot password and a less complicated login screen. But the de facto and what Google supports is essentially one key here. A quick word on Android credential storage. So the system credential storage allows for things like VPN keys, your Wi-Fi creds, asymmetrical keys that can be stored. These are encrypted from a key derived from the user's passcode. This can be hardware-backed. I sort of alluded to that earlier. Some devices have hardware-backed crypto such that even if you root your device, you can't use that to access the keys that are stored there, and thus requires the device and any attack that you want to do on the key store. Unfortunately, the key store has had a lot of issues in the past that are now largely mitigated in newer versions of Android. But as I mentioned, there's a lot of legacy Android out there that still has these issues. And application developers run into things where the things they store in the key store just disappear arbitrarily, or there's like inconsistent behavior and unclear documentation on how those things work. So we've seen, when I assess security apps, like for my job, a lot of developers try to hack around this and do their own thing, which usually ends poorly. So this is significantly improved with Marshmallow and now NuGet coming out. These behaviors are clearly defined, but there's been a long history of application developers not really being able to trust the key store, and so this introduces problems. A look at Marshmallow. NuGet's going to have some new changes, but since they're still in developer preview, not super relevant right now, but they implemented scrypt hashing of the unlocked passcode values. So this used to be done with SHA-1 MD5 hash concatenation. This has been replaced with something much more sturdy. And now the key store, like I mentioned, has some guarantees and some actual documentation from Google on how these things work. Additionally, now keys can have additional metadata attributes like, the application developer can say, you can't use ECB mode or you can't use fixed IVs, you have to do these more secure behaviors. So these can actually be set by the application developer. And lastly, the Nexus imprint. Similar to what Daniel was talking about with Touch ID, Google officially released their implementation of this, the reference implementation. And OEMs, for years before this had sort of had their own fingerprint unlock style things, like Samsung, for example, had this for a while. But this is a win for data storage because it allows you to have a much more complicated boot password that you don't have to type every time that you want to unlock your phone. So it encourages people to set something that's not 1, 2, 3, 4 to unlock their phone, and then they have the convenience of being able to get to their data when they get a new tweet mention or something like that. This can also be used for secure payments, and this data is stored securely in the trusted execution environment. The most important thing here is that it sort of defines the standards for OEMs to use on how the Nexus imprint is, so that hopefully people start using this instead of doing their own custom things. Google and their OEM partners have a long history of having different ideas on how to secure things, and unfortunately this leads to wild inconsistencies among devices you see out in the wild, especially among the cheaper devices that You can get very cheaply, but don't have a lot of protections because it costs money to implement things like that. So you run into very different things in bootloader security. The presence of hardware-backed crypto storage or not, as I mentioned, the existence of a trusted execution environment such as TrustZone may or may not exist on the device, the budget devices you're buying. And even the boot image type can't be agreed upon. So you see lots of different image types, and if you're starting to look at things like that and take them apart, you're going to see a lot of different behavior out there. And even more, different OEMs offer much different protection schemes. So some OEMs like HTC have eMMC write protection, for example. So even if you were to leverage a local root exploit and you want to overwrite a partition, that write will be silently discarded based on that. So you can't actually implement it in the same way as another OEM. If you were to hack their device in the same way, you could probably overwrite that partition. Some devices actually check boot image signature verification, and many do not, which we'll see in a minute. And then even bootloader types, they can be locked completely and have no capability to change any of the firmware. There's the more popular and luckily for us, locked but unlockable. So this is a more responsible way to handle things. And things like Nexus or Sony or there's a lot of other programs out there that allow you to responsibly unlock your bootloader and thus completely blow away all the user data. But then you have the capability to write your own custom firmware to your device. And then, sadly, we have permissive by default where they just don't care at all, and you can kind of write whatever you want to the storage. So this is actually a pretty difficult problem to solve for Google because they want their partners to have the freedom to develop their own software and put whatever they want out there that runs Android, but then you run into issues where having inconsistent security is gonna burn you. So it's really challenging for Google to enforce these consistent protections. And one of the nice things that came out with Marshmallow is that Google finally said, you have to protect the boot to some extent. So you have to put an option in developer options that the user has to go in and manually click a box that says, I am okay with OEM unlock. And so now there's a slight barrier to entry because then you have to know a user's passcode to get in to enable that option. But there's still a lot of people that just don't set passcodes on their devices and things like that. So as Daniel kind of alluded to earlier, Apple has a very distinct advantage here because they control the entire stack and they don't have to deal with one OEM doing something crazy and the other one doing something sane, but they all run Android. It's sort of just completely controlled by Apple in that regard. So let's talk now about the importance of boot security. We can kind of make some assumptions that the bootloader, there's usually a series of bootloaders that check the next level to see the signatures. So we can kind of call that secure. So we have that green. And then we have the user data partition all the way at the end, which if you've enabled encryption, we're calling that secure as well. But there's two things in the middle here that create a vulnerable boot chain trust issue on Android. And that is that many devices do not check the boot kernel or the system's integrity. So you can tamper with these. There's some protections now with DM Verity and things like that, but again, wildly inconsistent as to how these are applied. So we can kind of tamper with these things and then potentially just completely invalidate the whole full disk encryption. And so let's take a look at how that's possible. If you saw my talk last year here at ChakaCon about Android firmware images and building your own images, I talked a little bit about download mode. But this is a very scary thing that exists on every Samsung device. It's their own custom bootloader implementation, and internally Samsung uses a tool that's pretty terrible software called Odin. It's Windows only, but using this you can potentially overwrite any partition on the internal storage with a firmware image that you provide. And you can kind of enter this mode with what we call the grip of death. If you've ever messed with any Android devices before, you kind of have to hold a lot of buttons at the same time in order to get it to boot into a different mode. So this particular one drops you into a bootloader interface. And you should check out Heimdall, which is a reverse engineered version of Odin, but it's cross-platform and open source. If you're interested in working on some of these things, it's a lot nicer to get working than Odin. But it should be fairly obvious that this is terrible. This is overly permissive. There should be no way to overwrite these partitions on a device, at least without responsibly unlocking it first. So with a few exceptions, most devices allow direct write access to the internal storage. Verizon, notably, and AT&T have had restrictions for years on this, such that you could still actually do the write in download mode, but it would realize that the signature was different and fail to boot, or just completely brick you in the case of a lot of Verizon devices. But this exists internationally on all their devices and has really only largely been fixed in Marshmallow, where Google mandated that you have to click that box I mentioned earlier. Let's look at some other bootloaders. Little Kernel, which is used on Qualcomm devices, has had many issues in the past that allow similar functionalities. So, the boot command just completely bypasses signature verification. So you're not able to flash a new image persistently, but you can boot it once. And if you can do that, then you can tamper with anything on the system. And then it's actually worse because when you reboot, it's gone. There's other issues where you were able to forge signatures based on some crypto weaknesses they had. And then the newer one, when you flash sparse bundle images, it didn't actually check the end of where that sparse bundle was. So if you cleverly made something that overwrote a particular partition, you could still execute something like this. And then Laugh, which is very aptly titled because this is a hilarious backdoor that LG shipped on a lot of their phones. It's a special boot mode, very similar to download mode. And you talk to it with an obscure send command binary, which was Windows only, but somebody ported it as a Python script, so now it's cross-platform and open source. But essentially, you figure out which COM port your phone's connected to and provide that integer to send command, and it drops you into a root shell on the phone. So from that root shell, you could flash any image you want. You could access any data in the system, for example. And this actually shipped on the Nexus 5, which really surprised all of us when we kind of realized that this was possible on a Google device. So that was patched out, obviously. But LG's fix was fairly incomplete, so this is actually still possible on a number of models. Essentially what they did was they realized, well, we shouldn't allow overwriting these particular partition IDs because they contain susceptible firmware images. So we'll just block the ability to write to, for example, MMC block 0P1. But they didn't block the root volume, the root of the block device. So using DD and seek, you could cleverly write to MMC block 0 and then just find the offset for the partition you want to overwrite and still execute this bug. So this is obviously fixed now, but this is something that exists on a ton of handsets out there. So now we're going to talk a little bit about the exploit release last year. And we kind of want to revisit the idea that full disk encryption protects data when the device is turned off. And we posit that that's not necessarily true on a lot of devices. So this is Rosie, the evil Android, evil maid. This is a classic evil maid attack. Stuff like this has existed for a while. We just kind of put it together as a proof of concept here. But it exploits permissive bootloaders. So any of the previous slides, we just talked about ways to do this. You flash a custom boot image, overwrite the kernel. We backdoored the kernel, and in less than 2 minutes, including multiple reboots, the device is completely backdoored. So you do this, you give it back to the user, they type in their decryption key, and the sky's the limit at that point because we have kernel execution. So we could steal the encryption key, we could exfiltrate specific data off the device, you could get a shell, basically anything you want. For the purposes of the demo, we are exfiltrating a specific piece of data, but you could essentially do whatever you want with this. So Daniel's going to talk a little bit about the setup, and then we'll watch what happens.
So I want to put this all together. The first thing we did is using the permissive bootloader, which Drew mentioned, just for our development process. It's not really the exploit in the end, but just to get going with this, we installed a free recovery called TWRP, or TWRP, on there. We used Odin to flash that on the device. And once we had it, we downloaded the kernel source. for the device we were looking at. Since the licensing requires the kernel to be open source, we just could get it from the OEM's website. And we added our own custom kernel module to it. So here you can see our make menu config with our backdoor module enabled. So we added this to the kernel and compiled it. And then we just went through these steps basically until we got it going. We compiled the kernel, we put a boot image on the device, rebooted the device, and tested until we got it going, until we had a final image which would work. So and then once we have this, the exploit doesn't require these steps anymore. The only thing which needs to be done is what you're going to see in this video now.
All right, so we start with a popular device. It's on just to prove that we can turn this off and start the attack. In the lower right corner, you're going to see like a shot clock style timer to count how long this actually takes. So here I'm doing the grip of death I mentioned earlier to place this device into download mode, where it's very permissive. You get a warning that says modifying this OS could cause security issues, which should be self-evident. So we connect it to the tool, and we load our custom kernel into the right slot. And here in under 23 seconds, that device has been completely backdoored. So it's going to reboot. And then once it reboots, the user, assume that you've sort of given this back to the user. And Daniel will talk about what happens now.
Yeah, so the premise is we got access to this device for a short amount of time where you go through security somewhere, or I just borrow it while you're in the bathroom or something like that. And then the user gets the device back, and they're like, oh, it's off, and they need to restart it. They type in their passcode, and then the phone will regularly unlock, and our kernel backdoor will basically run. And here on the right side, you see a shell. It's just like a netcat listener somewhere on a cloud instance. And once the device is unlocked, we will see that it just dumps a hex dump of a file which we're sending out there. It's going to take a few seconds. There we go. So we got the file received on the cloud. And then you can see we're just checking, OK, there is actually a SQLite database there, which is the accounts SQLite database file. And we can use this SQLite to look at it, and we can look at all the files on there, on the tables. And then after this, we will quickly log in via ADB shell to show you that that file is actually a protected file. If you try to cat that file as a regular user, you will get a permission denied error because it's actually owned by root, and you should not be able to get to it. So this kind of shows we're running on kernel, at least root rule privileges, and we could get a file off the device which was full disk encrypted by backdooring the kernel like this. So just to review this real quick. So this is possible on a number of OEM devices. This is not particularly to this one. All of the ones where you don't have protection of the boot image, for example, and which have these permissional bootloaders, which Drew has been talking about. So this is not a new problem, and all this flashing of boot images has been used by the modding and by the rooting community before. And Google is aware of this, and I think Drew mentioned already that they're trying to prevent this by having a responsible unlock where you need to type in the passcode first before the bootloader is unlocked. And then finally, similar things are also possible on iOS. I mentioned the evil maid attacks briefly before. If you can jailbreak a device, and you can also modify the kernel or other code on there, and you can put a backdoor on it just the same way you can do it on Android. Just that the technique is a bit different there.
All right, so yeah, this is what we call the Drew's soapbox slide. So essentially, there's ways to fix this, and it requires cooperation with Google's OEM partners and Google. We want to see secure configurations by default. I mean, when you buy a device, it should be locked down as hard as possible. However, we believe there should be responsible bootloader unlock capabilities. I think a lot of these public exploits that come out simply exist because there's such demand that people want to legitimately modify their own devices and run rooted apps and change the way things look, right? So these exploits may not be as necessary to exist if the OEM partners just said, okay, if you accept the risks, we'll let you unlock it, and then you don't have to do these sort of dangerous hacks to your device. We'd really like to see clearly documented security guarantees because each device, you have to research each one individually. Even devices within so one OEM's device on different carrier networks will have different protections, and you don't really know that until you actually buy the phone and figure out how it works, because no one's no one's saying, here's what we're protecting. And we'd like to see consistency among these OEM partners. So, let's have one heavily audited public bootloader that we all agree to use and keep our eyes on to make sure there's no security vulnerabilities on. If everyone didn't do their own thing and have all these crazy problems with their bootloaders, then this problem would largely be mitigated in a lot of cases.
So let's get us to some alternatives to platform security. Maybe it becomes clear in a second what we mean by that. So what do you do if you're an app developer and you may not be able to enforce users to set passwords on their devices? So the most common solution for that is having custom app sandboxes. If you're familiar with Good or Mobile Iron or any of these container solutions, that's kind of what they do. You add a passcode to the application, just like what we've described in both cases. You derive an encryption key from that passcode. You encrypt all your data in the sandbox with that passcode. And whenever the app is being closed or backgrounded, you just wipe that key from the memory. And you should be having an implementation which is pretty similar to what the operating system provides. The problem is, though, getting this right is hard. So getting crypto hard is already hard. But on top of that, you also have the problem that you don't have any of the hardware support which the operating system has for you. So you don't have brute force protections or any kind of enforcement for how many attempts somebody could make, or you can copy the sandbox off the device and do an offline brute force attack and things like that. Another option would be potentially to not have offline storage at all and just have an app which stores everything online. But that's challenging too, because we need to have some applications which have offline data, and we have to have usability so that the user doesn't need to log into the application every single time they're trying to access their information. Because otherwise, you opened up an app, and if the app auto-logs in, then you didn't gain anything, right? Because you can still get the data. So you would need to have an authentication at each step of there. So where does this leave us? Just like two things here. In general, for best practices for users, we have to set strong passcodes on the devices so that the operating system we can actually use the hardware features and everything in there. And then for iOS, you might want to consider enabling remote wipe so that your phone gets wiped if you either remotely want to or if you're typing in the passcode a number of different times.
Yeah, and, real quickly for Android, choose your device wisely. This is not an easy task. You kind of have to research them. And encrypt your device if it's not forced. This has been a user electable option for many years. Like, please enable this. Best practices, determine if we have to store this data at all. This is case by case, obviously, but do you need to store this secure thing, or can you pull it down when you need it? Android relying on platform security is very challenging, as we've seen, and for iOS.
Yeah, for iOS, you want to use a protection class which actually requires a passcode, which incorporates the passcode into the encryption. And if you want to store data which is not which you are storing yourself as an app developer, you want to use one of the protection classes which actually makes use of the passcode and warn the user if they don't have a passcode set on the device if possible.
So our takeaways, security controls should be balanced with how sensitive the data is and the threat model. Remember the graph we showed earlier, who are you worried about? Protect the data until it's actually needed. And secure storage relies on the entire stack being secured, and hopefully the attack we showed earlier illustrates the importance of this. So we want to say thanks very much to Shaka Khan for having us. It's great to be back here. Any questions, please let us know. The slide deck should be available shortly at that URL after the talk, and follow us on Twitter and social media. But thanks very much to everyone.
Any questions? Yep.
Encryption of external SDs for Android in particular, similar mechanisms or manufacturer dependent?
So good question. That's actually changed with Marshmallow. There's what they call SD card adoption. So there's two methods that you can do. One is if you adopt it to the system, it gets formatted as ext4 and then is encrypted. And essentially, if your device gets stolen or lost or you forget your password, that data is as good as dead. So even if you take the card out and try to look at it, you're done. The other option is the historical FAT32 Valdi sort of like hack that they have, where it just treats it as a normal SD card, and then it doesn't have any of the OS level encryption protection. It's whatever is stored there, whatever application decides to store it there, it's up to that application to decide how that's stored.
I think there's somebody back there. Yeah.
The comment that you just made about the external drive, is that also for the new plug-in like the USB and device as well? For encrypting that data?
So like connecting something with like a USB OTG, is that the question, or? Yeah, so yeah, so you'll get prompted whatever you plug in as an external storage medium to either adopt it or let it be under the normal mechanism. So it'll work exactly like what I described to the previous question.
Okay. Well, thanks everyone.
Cool. Thanks, everyone.